Hi, Jasmine.
Hello, Professor.
Hi.
Hello.
How's it
So,
going?
I have a problem with the Discord.
The Discord? Okay. What's up?
Yeah, I can't access the other channels. I only see the announcement channel.
Let me see. Did you join? When did you join?
Like the first day of class.
What's your name on Discord?
It says Gibby right now.
I've assigned you a role. You can't. You only see the announcements channel.
Yeah.
Okay. Let me see. Okay. Try it now.
Let me restart my Discord.
Yeah. So, because usually when you first join, you should only be able to see the announcements. But then after I go in and I assign you a role, then you should be able to access the other ones. I do see some activity in at least the questions channel. So
Yeah, I still only see the announcements.
okay.
Should I try leaving the Discord and joining again?
Yeah, you can try that. Let's see.
Yeah, I just joined again.
Okay. Yeah, I just gave you the permissions. All right, see, try it again.
Okay, yeah, I see announcements, introduction, questions, and names.
Okay, great. Yeah,
Okay,
those are all the channels. Yeah, I guess maybe maybe it was still kind of weird when you first joined, but it's good. It's good that it works now.
Yeah, thank you.
Yep. It was good. Yeah, it was my mom's birthday last weekend, so I just went home and I cooked dinner for her. Besides that, just relaxed. My mom's happy this year because usually her birthday lands on the Super Bowl and everyone kind of forgets that her birthday exists. But this time her birthday was a week before the Super Bowl. I made her grilled chicken basically. So I grilled some chicken, then I made a like roasted potatoes and French onion soup. And my little sister is vegan also, so I had to make sure the potatoes and the soup were vegan. Obviously, she couldn't have the chicken, but the chicken was mostly for my mom. How was your weekend? Yeah, it's that time of year. I've had a lot of students say that they're applying for internships or they're getting interviews now. So yeah, best of luck for the interview. Oh.
Okay, got it. Okay. Since we haven't done this, what was the latest you needed confirmation by? Because I need to.
Professor, have you
Yep.
played Little Nightmares?
Little Nightmares? No. What's that?
It's a side-scrolling, 2D side-scrolling game, kind of like Mario.
Oh, okay. Is it on Steam?
Yeah.
Nice. Yeah, I never heard of it. Let me see. A little bit of time. What's it called again?
Little Nightmares. I can type it up.
I got it. Oh, so there's a 1 and a 2.
Yeah.
Oh, interesting. Oh, yeah, it looks interesting. How'd you find out about this?
It was from Steam. I've had it for I think a couple of years.
Oh, okay, nice. Yeah, if it's on sale next time, I'll check it out.
A question for you. Does MATLAB have a student version?
Wait a second.
Does MATLAB have like a student version of it, or is there like do I just use a third party similar to MATLAB?
So MATLAB, you can download it from the school, actually. Yeah. So
Okay.
if you search like Cal State Fullerton MATLAB, that's how I usually do it. And you log in with your Cal State Fullerton account, then you should be able to download it for free.
Okay, thank you.
Mm-hmm. All right, it's 2:30, so let's go ahead and get started today. All right, good afternoon, everybody. How's everyone's weekend? How's everyone's doing?
Literally didn't leave my room all of Sunday, but
I mean, that's the pandemic life, right? Everyone just kind of stays inside, but yeah, it's been like that for a long time. We just got an email today as faculty from the provost and said for fall they're hoping to return to in-person instruction, but they also said prepare for virtual if needed. So I think there's still a lot of uncertainty going forward, but yeah, I guess it's this is how we're going to be. Okay. So the plan for today is we're going to finish up our first set of lecture notes on conduction, specifically planar conduction. So today I'll do another example with the heat equation, just so you can see kind of a more complicated example with that. And then we'll go over probably one of the more important concepts of this class, which is thermal resistance. Okay. I posted the first homework assignment. So the first homework you can see on Canvas. And so if you haven't seen that already, definitely go check that out. After today's lecture, you should be able to do everything on that homework assignment. And it's going to be due a week from today. So it's going to be due on Monday, February 8th by 11:59 p.m. Okay. And so it's not due at the lecture, but you have until basically 11:59 to turn it in. Okay. And just be careful. So because, you know, I allow late assignments up to a week, I have the assignment actually open for a week after it's due. So you should see 2 dates there. So you should say due on the 8th, but then it'll say also available until the 15th. And all that means is that you can still turn it in late up until the 15th. But remember, you know, each day that you turn it in late, I have to dock 10% off the score. Okay. All right. So are there any questions I can answer before we get started today? Okay. Okay. So I think last time we left off doing an example with the heat equation, right? And so our heat equation is kind of our starting point for a lot of thermal analyses, because what this allows us to do, it allows us to solve for a distribution of temperature inside a medium. Okay. Because usually, you know, in heat transfer, if you can solve for the temperature field, or you can see, you know, how temperature varies in a solid, that's usually a great first step towards doing a lot of thermal analysis. Okay, and the heat equation is kind of where we first started, and we didn't run through the derivation, but basically the heat equation is a result of doing conservation of energy. Okay, and so mathematically, the heat equation looks like this. And so we had a double derivative of T with respect to X, okay, plus Q dot over K, where that second term is our thermal generation term. And then we have our unsteady term over here, okay. All right. And so last time we did an example where we solved kind of the simplest case where we canceled out the second 2 terms. So we said there was no thermal generation and no unsteadiness. And so today I wanted to start with a little bit more of a more complicated example where we are going to consider this thermal generation. Okay, we're still going to ignore unsteadiness just because, you know, that's a topic for a few weeks from now. But, you know, I want to show you at least how thermal generation comes into play. Okay. All right. So let's do another example. Okay. All right. And so in this case, we're still going to have a planar wall. Okay. Okay, and so schematically, it's going to look the same as the almost the same as the last one. Okay, and so we're going to have 2 walls right here. Okay, this left-hand side is going to be our you know, our x coordinate is going to be 0 on this left-hand side here. Okay, okay, and on the right-hand side, we're going to say the x coordinate for that is going to be L. Okay, and this example here has some numbers, and so this L is going to be 50 millimeters. Okay. Okay. And so on the left-hand side here, we have 2 known things. Okay. So first of all, we know that there's some convection. Okay. Right. Anytime I draw basically 3 arrows like that, that indicates that we have some moving fluid past our surface, and then we're going to have some convection cooling. Okay. And so the statistics for the convection, or the parameters, right, to say, is that we have an ambient temperature, or T infinity, of 20 degrees Celsius. Okay. And so all that means is that the temperature of the fluid that's flowing past is 20 degrees. So that's about room temperature, a little bit cooler than that. Right. And then our convection coefficient, which we're going to use to plug into Newton's law of cooling, is going to be 500 watts per meter squared. Okay. And so that convection coefficient, you can basically think of it as how effective this fluid is at transferring heat. Okay. And so 500 is a pretty good number right there. Okay. Okay. Another thing that we know is we also know the temperature of this surface right here. Okay. And so this temperature is going to be 120 degrees, and we'll call that T naught. Okay. And on the right-hand side here, we have a surface that's perfectly insulated.
Professor, is after the T infinity, is that H equals 500?
Yes. Yeah. So H is the name that would call the convection coefficient.
Got it. Thank
you. Okay. All right. So when you're doing these problems, you know, and you see these kind of like diagonal splashes onto a wall, that usually means that it's perfectly insulated. So most of the times, you know, the problem will tell you that the surface is insulated, but you know, anytime that it doesn't say that, but you see these splashes, you can assume that it's insulated. Okay. Okay. And so another thing that we know is we know the thermal conductivity. And so the thermal conductivity is going to be 5 watts per meter K. Okay. And then what's unique about this problem is that we're going to have some thermal generation. Okay. And so remember, our thermal generation is represented by the symbol Q dot. Okay. And in this particular case, it's unknown. So that's one of the things we're going to solve for in this problem. Okay. Okay. And so remember, thermal generation represents any heat or any kind of energy that's being created within this medium. Okay. And when I say, remember, when I say energy that's being created, what I mean is strictly thermal energy. Okay. Because we know that, you know, there's no way for energy to be created or destroyed in the world, but energy can be transformed from one form to another. Okay. And so when I say that there's thermal generation, what I mean is that there's probably some kind of either chemical reaction going on in the solid, which is, you know, transforming chemical energy into heat. Okay. Another popular form of this is electrical heating. Okay. And so what can happen sometimes is that you can have, you know, heating wires that are coming through this this all throughout this solid, and then the electrical current from the wires is you know, heating up the solid from the inside. Okay. But mathematically, we can just sum it up in one particular term, which is thermal generation. Okay. Okay. And so in this particular problem, what we're interested in is not only to solve for this thermal generation, but also to solve for the temperature distribution as well. Okay. And to do that, we're going to solve the heat equation, which is what I have above. All right. Okay. Any questions on the problem setup so far? Okay. All right. And so in these problems where you're asked to solve for the temperature distribution, your starting point should always be the heat equation up here. Okay. And the first step to solving these heat equation problems is to apply some assumptions. Okay. And so we're given one very big assumption in the problem. Okay. And it's the fact that it's steady state. Okay. Anytime you see steady state, you can automatically cancel out any derivatives with respect to time. Okay. And so I've already kind of done that. And so basically we can cross out this guy right here on the right. Okay. And so all that we're left with is the second derivative of t with respect to x plus q dot over k, right? And then what we can do from here is move q dot over k to the other side, and then just start integrating and then solving for the constants, okay? All right, so let's go ahead and do that. All right, so if you move q dot over k to the other side, we have d squared t over dx squared is equal to minus q dot over k, okay? And so let's integrate this guy. Right? And so we integrate once. We're going to assume q dot is a constant here, okay? And so if it's just a constant, we have q dot, which is a constant, over k, which is a constant. And so we just end up with q dot over kx, okay? And so we have dt dx is equal to minus q dot over kx, okay? Plus c1, remember we have to add our arbitrary constant, okay? Okay. And then now that we're in this form, we can just simply integrate again, okay? And so we integrate again, we end up with t of x is equal to minus q dot over 2k x squared plus c1x plus c2. Okay. And so this is our temperature distribution here, but we have three unknowns, right? And so we still don't know what q dot is, and we don't know c1, and we don't know c2, right? And so in order to solve for these, we have to apply the boundary conditions. Okay. Okay. All right. And so let's go back to our previous diagram here and let's view all our boundary conditions. Okay. And so we have three here. So the first is a simple specified boundary on the left-hand side. Okay. That's going to be T naught is equal to 120. Okay. And so we have T of 0 is equal to T naught, which is equal to 120. Okay. All right. And so let's go ahead and apply this one, because this anytime you have a boundary condition at 0, that's usually a pretty good place to start, because that's, you know, by plugging in x is equal to 0, that usually cancels out a lot of stuff. Okay. And so let's plug in T of 0 is equal to minus q dot over 2k times 0 squared plus c1 times 0 plus c2 is equal to 120. Okay. We have q minus q dot over 2k times 0 squared, and so that's going to be 0. We have c1 times 0, which is going to be 0. And then all we're left with is c2 is equal to 120. Okay. And so that's the first constant down. So we've already solved for that one. And so now we can go ahead and solve for the other ones. Okay. And so, you know, just kind of general problem solving tips for this one. If you have a boundary condition at 0, you should use that, because that's going to be, you know, the most useful. Okay. Okay. And so we actually have another boundary condition at 0 here, which is going to be our convection boundary condition. Okay. And so remember, for convection boundary conditions, we're going to apply Newton's law of cooling. Okay. Okay. And so the formula form for this is going to be, we have minus k. Okay. dt dx at x is equal to 0. This is equal to h times t infinity minus t at 0. Okay. And so this is the form of the convection boundary condition that we talked about last time. Okay. And so now all we have to do here is start to plug in for all of these parameters here, because we have everything that we need here. You know, we just have to plug it in, and then we can use that to solve for another one of the constants. Okay. Okay. Any questions on this before I turn the page? And so plugging in, we have dt dx, or we have minus k times dt dx at x is equal to 0. Okay. And so if we go back up here, we have an expression for dt dx right here. Okay. And so let's go ahead and plug that in. Okay. And so dt dx is minus q dot over k times x, okay, plus c1, okay. And then we're going to evaluate this at x is equal to 0. And so that means we're going to plug in x is equal to 0 in there. Okay. And this is equal to h, where h we know from the problem is 500. Okay. And then we have T infinity, which is the temperature of the fluid. And so the temperature of the fluid is 20 degrees C, okay? Minus the temperature at 0, which we already determined from the previous boundary condition is 120, okay?
Professor?
Yep.
I thought there was a 2 underneath the q dot over 2k. Is that?
Yeah. Good observation. So in our temperature solution, there is a 2 right there, right? And that 2 came from integrating this guy up here, right? But in this convection boundary condition, what we're plugging in for is not T, but we're plugging in dt dx, right?
Oh.
And so
okay.
in dt dx, there's no 2 down there.
All right, sorry about that.
Yeah, no problem. No, it's tricky. Yeah, it's you definitely have to be a little bit careful here because it's you know, those little numbers like that, they can kind of sneak in and sneak out. So it's definitely good to be explicit with that. Okay, and so let's go ahead and plug in x is equal to 0 here. Okay, and so we have minus k times q dot over k times 0, which is just going to be 0. Okay, and we can plug in for k too. So k is 5. Okay, and so all we're left with over here is just c1. Okay, and then on the right hand side right here we have 500 times 20 minus 120, which is minus 100. And so we end up with minus 50,000. Okay. We can then divide both sides by minus 5. And we get C1 is equal to 10,000. And the units for this is going to be degrees C over meters. Okay. Right. And so that's 2 of our constants. And so that's good. Okay. And so we can go ahead and cross this guy out. And so the last constant that we need to solve for here is q dot. Okay. And luckily for us in this problem, we have a third boundary condition that we can apply. And that third boundary condition is the fact that it's perfectly insulated on the right-hand side. Okay. All right. So let's go ahead and apply that boundary condition. And remember, when something's perfectly insulated, we basically say that there's no heat transfer on that side. Okay, and so mathematically, the way that we can express this is by saying that the derivative of temperature with respect to x evaluated x is equal to L. Okay, this is going to be 0. Okay. Notice the difference here. So on the convection boundary condition, we evaluated it at x is equal to 0. Since the insulated boundary condition takes place at x is equal to L, we're going to plug in that one. Okay. All right. So let's go ahead and plug in for dt dx. And so dt dx is minus q dot over k times x, okay, plus c1. And all this is equal to 0. Okay. Okay. And from the problem, we know that L is equal to 50 millimeters. If you convert that into meters, L is going to be 0.05. Okay. And so if we look at this mathematical expression here, we're going to have everything that we need to plug in except for q dot. Okay, and so we can use this expression to solve for Q dot. And so we have minus Q dot over K. K is 5. Okay, we know L is going to be 0.05. Okay, plus C1, where C1 we just got from the previous part. C1 is going to be 10,000. Okay, all that's going to be equal to 0. Okay, you perform a little bit of algebra here and you solve for Q dot, and what you get is Q dot is equal to, looks like 1 million. Okay, and the units for Q dot, which is the units for thermal generation, is going to be watts per meter cubed. All right. And so now we have Q dot, we have C1, and we have C2. And now we can just plug all these guys in and solve for our entire temperature distribution. Okay. And so the last step in this problem is just to write out T of X. And so T of X is equal to Q dot minus Q dot over 2K. And so if you plug in all those numbers, you get 100,000. Okay. X squared with a minus sign. Okay. Plus 10,000. X plus 120. Okay. And so here is our final temperature distribution. Okay. Right, so this problem was a little bit unique because we had 3 unknowns. And so usually when you're solving heat equation problems, you only have 2. So you just have C1, C2. But in this case, we had a third unknown, which was Q dot. Okay. And so in that case, we had to, or the problem had to give you an extra boundary condition for you to apply in order to solve for that Q dot. Okay. All right. Any final questions on this example here? Okay. All right. So that's the heat equation. Okay. So we saw, so we've seen, how we can use the heat equation to solve for temperature distributions. And we've seen kind of 2 examples. So we saw one kind of pretty simple example and another example where, there's kind of a lot more thrown in there. Okay. And so, for the homeworks and for the exams, you can kind of, expect these problems to be kind of on the spectrum of these kind of 2 problems. Okay. Okay. And so now, now that we're done with the heat equation, I'm going to switch gears a little bit. And so we're going to talk about this idea called the thermal resistance. And so the idea with the thermal resistance is to kind of simplify your thermal analysis, okay? Because in the methods that we just shown previously, like heat equation's fine, heat equation's really great actually, but sometimes we want to perform some calculations without having to solve a differential equation, right? Okay. Because the reality is, heat equation, even though it gives you a wealth of information, right? And so, this previous, temperature distribution that I've shown up there will be able to tell you what the temperature is at every single location inside your medium, okay? Which is great. But sometimes that's a lot more detail than we want. So sometimes we only want the temperatures at certain discrete locations, okay? And so in particular, one temperature that's almost always relevant for thermal analysis is the surface temperature, right? Especially if it's going to be for a device that's going to be handled by people, right? Because it's people usually want to know that if they're going to touch something, whether they're going to burn themselves or not. That's usually something that's good to know, right? And so in order to get that information, we don't have to go through the whole thing of solving what the temperature is, 5 feet into the wall, when most times that doesn't matter. Okay. Another area where you'll see thermal resistance comes into play is that it's really good at dealing with composite structures. Okay. Okay. Or in particular, composite kind of means a lot of different things nowadays. And so when I say composite structures here, what I mean specifically is layered materials. Okay? Okay. And so let's say that it's something that looks like this. Okay. Okay. And so let's say that we have a structure that looks like this, where we have a temperature on the outside here and a temperature on the inside. Okay. And then separating these two temperatures are different layers of material, right? And so maybe this is material A, this might be material B, this material C, and this is material D. Okay. And so, just because we have just for the fact that we have a temperature difference here, let's say that the inner temperature is higher than the outer one, the heat is going to travel across all of these different surfaces. But if you wanted to solve this with the heat equation, you would have to solve the heat equation 4 different times, right? And so you'd have to solve the heat equation in material D, okay, and then apply 2 boundary conditions. You'd have to solve the heat equation in material C, apply 2 boundary conditions, okay, and then apply it in material B, 2 boundary conditions, and then material A in 2 boundary conditions, okay? And so you can do that, that's totally fine. It's just, most people have lives that they want to return to and not just solve the heat equation all day, okay? And so with thermal resistance, it makes doing analysis on these systems, much, much easier and much simpler, okay? And so, basically what we're going to do is we're going to reduce our kind of differential equation problem into an algebraic one, okay? And that's going to simplify our lives quite a bit. Okay, any questions on this? Okay. All right, and so how do we actually perform, or where does this, how do we even start with thermal resistance? Okay, and so our starting point actually is going to be our example that we ended with last time, okay? And so last time, if you remember correctly, we had a situation like this, okay, where you have just kind of one layer of solid stuff, okay, and then on one side we had a certain temperature, okay, and so say that out here we had an outer temperature, so we'll call that TO. On the inside we had an inner temperature TI, okay. And then from this situation, we found that our temperature distribution was something like this. Okay, so we had Ti minus To over L. Okay, where L is the width of this wall, okay, times X plus To. Okay. Okay. And so basically that's just a linear variation of temperature across the surface, okay? Let's take this temperature distribution and find the heat transfer rate. Okay. And if you remember, our formula for heat transfer rate is going to be Fourier's law. And so heat transfer rate Q is going to be minus Ka dt dx. Okay. And so let's go ahead and plug that in here. Okay. And so we have Q is equal to minus Ka d dx of this guy right here. And so we have Ti minus To divided by L times X plus To. Okay. And so if we take the derivative of this with respect to X, To is going to go away. This X also goes away. And so we have Q of X is equal to minus Ka, or K, let's do Ka over L times To minus Ti. Okay. Okay. And usually, you know, for these problems, To and Ti, we assume that they're constants with time. Okay. And then everything that we have in front here, this K times A divided by L, all these guys are constants too, right? And so basically, you know, for a case where we have specified temperatures on both sides of our material, we have a constant heat transfer rate throughout, okay? And so in cases where we have a constant heat transfer rate, you know, we can leverage this to kind of simplify our calculations. Okay? All right, question in the chat. So shouldn't it be Ti minus To? Yes, yeah, so there's a negative sign now in front. So I just incorporated that negative sign and swapped the order of those terms. Yep. Okay. And so now that we have the heat transfer rate in this form right here, I kind of want to separate it into two different terms. Okay. First, we have this guy, this Ka over L. Okay. And I want you to kind of notice something about this term, right? Remember, so K, remember, is the thermal conductivity of the material. A is the cross-sectional area, and L is kind of the thickness of the material. Okay. And so what's the reason I kind of grouped these guys together and I circled them is that all of these are strictly just properties of the material or of the medium. Okay. Okay. Whereas on the other side, this To and Ti, these are strictly conditions on the outside of the material. Okay. And so these are the surface temperatures. Okay. And so, you know, when we break it up like this, you know, we have a term that's strictly just the material properties or the physical properties of the material, and you have another term which is the outside temperatures. Okay, and so if we kind of you know look at it this way, this term right here, or the physical properties, you can almost think of this as kind of like a resistance to heat transfer. Okay. Because remember what we talked about last time in terms of thermal conductivity, right? And so depending on what kind of material that you have, that's going to affect how much heat transfer is going to occur in your, you know, in your solid, okay? And so that's encapsulated by K, but we also have geometric properties that are also important here too. So we have the area and the length, okay? And so basically everything physical that the material can have that can, you know, either improve or decrease heat transfer is all encapsulated into this one kind of product right here, okay? And so if we kind of lump them all together into resistance, then, you know, then we can use that idea to kind of simplify our calculations, okay? Okay, and so basically we're going to call this term right here. I'll do it on the next one because it's you know I'm running out of space here. Okay. So are there any questions on this before I turn the page? Okay.
Is this for static, dynamic, or both?
This is just for statics. Yeah, that's a good distinction. So once we later on when we do transient heat conduction where it's unsteady, this resistance doesn't apply. But for steady state, you know, we can use this. Okay. And so let's rewrite our heat transfer expression on the last page, but let's do it in terms of our our resistance. Okay? And so if we say we have this new variable R, so this R here is resistance. Okay. And we define this R to be L times K over A. Okay. We can rewrite our heat transfer expression. Okay. And so now our Qx is equal to 1 over R, okay, times TO minus TI. Okay. And so if we kind of lump this together, we can say this is the TO minus TI all divided by R. Okay. And so I write it in this form because, you know, typically when you think of resistance, you think of things that are impeding, you know, impeding stuff, right? And so it's important to have resistance on the denominator here. So the higher our resistance, the less heat transfer that we have. Okay. Okay. And so once again, you know, let's look at this expression for resistance up here. Okay. And so for this expression here, we have L in the numerator. Okay. And so what this tells us is the thicker our material is, or the longer it is, the more resistance we're going to have. Okay. Okay. And so intuitively that makes sense, right? And so let's say that, you know, you have a very hot surface, right? Would you feel more comfortable touching or, you know, putting on a glove that, you know, is as thin as paper? Or would you feel more comfortable putting on a glove that has a very thick layer of thermal insulation, right? You would feel more comfortable with the thicker one because that's going to prevent more heat transfer from getting to your from going from the surface to your hands, right? And so basically one way that you can increase resistance is just to put more material there. And that's what L is going to do, okay? In the denominator for resistance, we have thermal conductivity, okay? And so the better, basically the more conducting your material is, then the worse it's going to be at resistance, right? And so if you think about your materials that have traditionally high thermal conductivities, like metals, right? So metals are very good conductors of heat. And so those have very high Ks, okay? And so if it has very high K, then its resistance should be pretty low, okay? You can almost think of thermal conductivity and resistance as kind of almost opposite things, okay? All right, and then the last thing that we have here is the area, okay? And so the area, remember what we talked about before, basically the more contact area that you have, the more chances that heat's going to transfer, okay? And so it makes sense that A is in the denominator, okay? And so this resistance right here, this is the thermal resistance. For conduction through a solid. Okay. All right. And so the reason it kind of has this name resistance is it kind of borrows a lot from circuits. Okay. And so probably you guys might have seen circuits before in maybe a physics class or something. And I think, you know, you guys take a circuits class too. But in circuits, we have the very famous Ohm's law, right? Okay. And so in Ohm's law, basically what we have is that the amount of current that goes through a resistor, is equal to 1 over the resistance times the voltage difference, right? Okay. And so the idea of thermal resistance is basically the same thing. It's just that we kind of replace some of the terminology, okay? And so in heat transfer, what we have instead of current, we have heat transfer rate. Resistance, has this meaning that we just talked about. And instead of voltage difference, what we have is temperature difference, okay? And so that's kind of where we borrow this idea from, and that's kind of where it gets its name, okay? And so there's a very strong correlation between them. So if you have kind of a lot of intuition that you built up from circuits, you can definitely use that here as well, okay? Okay, any questions on this? Okay. And so that's a thermal resistance for conductive heat transfer. We can actually also form a thermal resistance for convection as well. Okay. Because recall for convection, our formula that governs that is Newton's law of cooling. As we have Q, convection, is equal to HA times T surface minus T infinity, okay? Right. And if we kind of break this apart like we did the previous one, you should see the form is kind of the same, right? And so we have H times A here, where H times A here is the basically the physical properties of the fluid, okay? And on the right here, we have a temperature difference, right? And so these are simply just surface temperatures. Okay. And so we can apply the same kind of logic here and come up with a thermal resistance for convection. Okay. And so if we take this, this term circled in purple and then turn it on its head, so we invert it, we have 1 over H times A. Okay. And so if you have any kind of convection in your system and you're given H and you're given A, then you can come up with the resistance according to this formula right here. Okay. Okay. And so now we have basically two formulas for resistance. So we have resistance for conduction and we have resistance for convection. Okay. Then let's do some very quick, simple examples just to kind of show you how you would actually use this in practice. Okay. Okay. And so let's take our example that we did at the end of class last time, and let's draw basically its thermal resistance and it's what I call its thermal circuit. Okay. 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 And so let's say that we have just a wall or a planar surface like this, okay, has a length of L. It has a thermal conductivity of K and an area of A. Okay. And so from this, we can transform this into what's called the thermal circuit, okay? And so instead of a wall right here, we're going to put a resistor. Okay. And so on both ends of the resistor, we have the temperatures, right? So on one side, we have TO. On the other side, we have TI, okay? And our resistance in this case, which is L over K times A, okay? And so from this information, we can say that Q, which is our heat transfer, is going to be 1 over R, where R is given right there, times TO minus Ti. Okay. All right. Notice it's kind of a subtle thing here, but notice how I put TO on the left, right? So I put, TO first, right? And so for these thermal circuits, the way I usually like to read them is just simply left to right, okay? And so if you're kind of consistent in that sense, then the signs kind of work itself out, okay? And so if you have a case where TO is higher than TI, then Q is going to be positive, and so that tells us that heat transfer is going to go from left to right. But if TI is greater than TO, then Q is going to be negative, and that means heat's going to transfer that way, okay? And so as long as you're consistent in terms of like how you list the terms in what order, then the signs kind of just work themselves out, okay? So the signs can be confusing, but the important thing with the signs is just to kind of be consistent on how you order the terms, okay? Okay, any questions on this?
I had a question. Will we be given problems where we had like multiple like thermal circuits or like for like multiple resistors?
Yep. Actually, that's going to be the next thing that we're going to demonstrate. So, yeah, definitely, that's where thermal circuits definitely shine, because it definitely helps in those cases. So next we'll do an example with the series circuit, and then we're going to do one with the parallel circuit as well. Yeah.
Okay, thank you.
Mm-hmm. Okay. All right, so let's do exactly that case. So let's do a case where we have actually we'll do a case with convection and also a layered surface. So this is a kind of a complex kind of composite. Okay. And so let's say that we have a material that looks like this. Okay. And so let's say that we have three materials. And so this material will be material A. And so it has thermal conductivity Ka. It has length La. Okay. The second material will be material B. And so it has Kb and Lb. Okay. Right. And then we have a third material here, C. Okay. So it has its own thermal conductivity and length as well. Okay. All right. And so let's say that this composite is being cooled by a fluid on both sides. Okay. And so on the first side, we have fluid 1. Okay. And so fluid 1 has its own H, and also has its own ambient temperatures. We'll call that T infinity 1. Okay. And on the right side here, we have a second fluid. Okay. And this has its own H and also its own ambient temperature. Okay. Okay. And so normally, if you wanted to solve this with the heat equation, this would be kind of a big pain in the butt. Okay. And so to kind of simplify this, we can just draw a thermal circuit for this guy. Okay. Where a thermal circuit has 5 resistors. Okay. And so we're basically going to make a resistor for every layer of material here and for every convection fluid. Okay. Okay. So let's do the fluids, the fluid one first. Okay. Okay. So that's going to be our fluid 1. Okay. And so then we're going to have a resistor for material A. So we'll call this material A, resistor A. Okay. Then we have a resistor for material B. So we'll call that RB. Then we have a material for a resistor for material C. So we'll call that RC. Okay. Right. Then we have a resistor for fluid 2, okay? And then on the ends of the circuit, we have our temperatures, okay? And so in fluid 1, this temperature at this node right here is going to be T infinity 1, okay? And then the temperature at this node right here is going to be T infinity 2, okay? All right. And so now that we have this circuit, we can go ahead and write an expression for the heat transfer, okay? Before that, we can write an expression for the total resistance, okay? And I'll do that on the next page. Before I do that, does this make sense? How we can take kind of a complex layered surface like this and turn it into a thermal circuit? Okay. Okay. And so now let's write an expression for the total resistance. If you remember from your circuits class, when you have resistances that are all in series like this, we can just simply add up all the resistances. And so the total resistance here is going to be the sum of our fluid 1, okay, plus our A plus our B plus our C plus our fluid 2. Okay. And if we plug all of those in, then we plug in the parameters for all these guys, we get for our fluid 1, we get 1 over H1A plus LA all over KAA plus LB over KBA plus LC over KCA plus 1 over H2A. Okay. And so that's going to be our total resistance. Okay. And so now that we have the total resistance, we can compute the total heat transfer.
What's A again?
A is the cross-sectional area. And so that's kind of the cross-section between the materials. Okay. And so our total heat transfer is just going to simply be Qx, which is equal to our two end temperatures here. So our two end temperatures are going to be T infinity 1 minus T infinity 2 all over our total. All right. And so with that, it's a lot of arithmetic because you got to plug in a lot of numbers for our total. But then we arrive at an expression for the total heat transfer, without having to solve for the heat equation. Okay. All right. One other thing that you can do with a circuit like this is you can use it to actually compute the temperatures on the inside. Okay. And so let's say that we come back to our diagram here. We're interested in what the temperature is at this interface right here. Okay. Right now we can't do that because it's they're not at the end temperatures. Okay. But what we can do is first we can compute this total heat transfer. Okay. And then what we can say is that this heat transfer here is going to be constant throughout this entire circuit, okay? And if that's the case, what we can do is we can draw a smaller circuit where we basically make sure that this surface temperature right here between A and B is one of our end nodes, okay? Okay. And the reason we want to do that is because when our target temperature is an end node, then it's going to show up in the equation as something that's like this, right? And if we assume that Q is the same from when we solved it before, we plug in for that. We have a new total resistance because our circuit is smaller, okay? But we can compute that. And then we have our first temperature here already. And so the only unknown in that equation will be that interface temperature there, okay? And so let me just show you how to do that, okay? And so in that particular case, you know, we had a situation like this, right? And we were interested in this temperature right here. And so remember, this is material A, and now here we have fluid 1. We'll call this TAB, okay? And so from here, we're going to draw a smaller thermal circuit, okay, where this is our fluid 1, and this is RA, okay? And on the endpoints of the circuit, we have T infinity 1, and we have TAB, okay? And so we can write an expression for the heat transfer just like before. So we say that Q is equal to T infinity 1 minus TAB divided by the total resistance for this circuit alone, okay? And so for this circuit alone, we only have 2 resistances here. So we have our fluid 1 plus RA, okay? Where this Q right here, this is the same as our full circuit. Okay, and so we can plug in just for that. And then we can use this expression here. So since now that Q is a known, we can then use this expression to solve for TAB, okay? All right. Okay. And so that's how you use thermal circuits for a series, okay? And so now let's see how we can do this for resistors in parallel. Okay? Okay. And so resistors in parallel, you might have a situation that looks like this. Okay? And so let's say that we have a material, okay? But then our material is split like this, right? Right. And so we have material A on the left-hand side, so that takes up the entire kind of width, okay? But then we have B and C, which are kind of stacked on top of each other, okay? And so let's say that in this situation, we can have heat that either flows this way, or we can have heat that flows through material C on the bottom, okay? And so in this case, where the heat can kind of take 2 different paths, we can represent this as a parallel circuit. Okay. And so in those situations, you know, we can, you know, represent it as 2 different resistors in parallel, and then we can use, you know, our rules for parallel resistors to help us compute the total resistance. Okay. Okay. Any questions on this before I turn the page? Okay. Okay. And so if we draw the thermal circuit for this guy, it would look something like this. And so let's say that we're starting from the left and then we're working our way to the right. Okay, so on the left-hand side, we first have our resistance for material A. Okay, and so this will be RA, just like that. Okay, and then after RA, you know, our material splits. And so we can either go on path B or we can go on path C. Okay. Okay. And then after that, after B and C, then we reconverge on D. Okay. And so our thermal circuit looks something like this. Okay. All right. And so whenever you have resistances in parallel like this, it's always really useful to combine them so that, you know, you don't have to kind of deal with it. Okay. Okay. And so if we combine these guys in parallel, you know, we can make just kind of one resistance for it. Okay. And if you remember kind of your rules for parallel resistors, it looks something like this. Okay? And so you have 1 over RBC. Okay. And so RBC, this will be our, you know, our combined resistance between B and C. Okay. Right. And so this is going to be the sum of 1 over all of the other resistances. Okay. So this will be 1 over RB plus 1 over RC. Okay. And so what we want to do is we want to combine these two guys. Okay. And so we're going to put them under a common denominator. Okay. And so our common denominator in this case is going to be RC. Okay. And so we have 1 over RBC is equal to, okay, RC over RB RC, okay, plus RB over RB RC. Okay. And then we can simply add these together, and this is going to be RC plus RB, okay, RB, RC, okay. And then to get the 1 over RBC, we can just simply invert this guy, okay. And so we get RBC is equal to RB, RC all over RB plus RC. Okay. And so that's just kind of, you know, basic how you combine resistances in parallel. Okay. And so now that we've combined these in parallel, you know, we have a new circuit here. And so our new circuit looks something like this. Okay. And so we have RA like before. Then we have our combined RBC, okay, and then we have RD, okay. And so now all we have here is just 3 series resistors, and we can just add them up, okay. Okay. And so we have our total resistance is going to be RA plus RBC plus RD. Okay. And then from there, we can compute things like, you know, total temperature or total heat transfer. Okay. And so in cases, you know, when you have kind of parallel paths like this, you know, you can use parallel circuits to to model them. Okay. And when you have parallel circuits, a lot of times it's most convenient to just kind of combine them into one resistance. So you just have kind of one path that you need to worry about. Right. Okay. Any questions on this? Okay. Okay. So there's one more concept I want to go over before we do kind of a more sophisticated thermal resistance example. Okay. And that's the idea of contact resistance. Okay. And so, you know, for the last two examples that we did, you know, we basically have different materials that were kind of stacked on top of each other, right? So they were making contact. We kind of assumed that, you know, what the contacts between them were perfect. Okay. That means, you know, there's no added resistance from having two materials, you know, next to each other. Okay. But, you know, what can happen sometimes is that if you have kind of two very different materials, let's say that you have like concrete and a plastic, right? And so the concrete kind of has a very rough surface and the plastic is very smooth, right? And so they're not going to make kind of perfect, you know, flush contact with each other. Okay. And so whenever you have those kind of cases where, you know, you don't have, you know, perfect contact, there can be some additional thermal resistance that's associated with that. Okay. And so visually, you know, it might look something like this. Okay. And so let's say that we have two materials here. Okay. And so material A, material B. Okay. And so, you know, just for the sake of this example, let's say that material A is concrete, you know, very kind of rough on the outside, and material B is plastic. Okay. And so if you zoom in at kind of the intersection between them, you know, it might look something like this. Okay. So A is on one side, B is on the other. Maybe B has kind of a very smooth kind of surface like this. But since A is concrete, you know, it might look, you know, something rough like that. Okay. And so they're not kind of making perfect contact. So there's kind of a lot of empty space in between these guys. Okay. And so in these situations, you know, the way that you can model this is you can put basically an additional resistor into your circuit. Okay. And so for your, you know, for this system, which looks pretty simple, you know, you can add basically a third resistor for this. Okay. And so our thermal circuit might look something like this. Okay. And so our two resistors on the ends, you know, we know those already. Okay. And so those will be the conductive resistances associated with material A and the conductive resistances associated with material B. Okay. And so this will just simply be L over Ka. Okay. Both RA and RB. Okay. But in addition to that, you know, we're going to have an additional contact resistance in the middle. Okay. So we usually call this R contact. Right. And so usually there's no formula for this because it really depends on kind of the microscopic, you know, contact in between the two. And so the way that you usually find this contact resistance is that you look them up in a table. Okay. And so, you know, there's a lot of these tables that you can find online. So if you search up, you know, thermal resistance between plastic and concrete, you know, you'll see some of the experiments that people have done where they can quantify these things. Okay. And there's some in the book too as well. Okay. For the purposes of this class, most of the time, 99% of the time, if I do give you a problem with contact resistance, I would just tell you what it is in the problem, okay? Because there's kind of no way to kind of compute it otherwise, okay? But I do want to let you know that typically you would look these up in some kind of table. Right? But in a lot of other situations too, a lot of time this contact resistance is really small compared to some of the other resistances. And so in those situations, you can kind of ignore it. Okay. And so for most problems, if the problem doesn't say anything, you can assume that, there's a very negligible contact resistance, or you can ignore it. Okay. It's only when the problem kind of explicitly says that, there's going to be contact resistance here. That's when you need to kind of account for it. Okay. But in reality, the contact resistance is always there. Just like, friction is always there, air resistance is always there. It's just a matter of, how influential is this going to be compared to some of the other factors. And the reality is a lot of times this contact resistance is pretty negligible. But for certain situations, it can be pretty large in comparison. So, it's good to kind of be aware of it and, and to know how to account for it. Okay. All right. Any questions on this? Okay. So I do have one more example to kind of show you kind of how thermal circuits are used kind of end to end on kind of a more complicated problem, but we only have 3 minutes left. So I think I'll save that for next time. Okay. And so I'm going to end the lecture for today. And then on Wednesday, we're going to pick it up right here and do kind of a more complicated example with thermal circuits, just so you can kind of see, how it can be used kind of more practically. Okay. And so with that, we're going to sign off for today. So thanks everyone for tuning in again. Hope you guys have a good rest of your day, and I'll see you on Wednesday.
Thanks, Professor. Have a good day.
Thanks, you
Thank
too.
you, Professor.
Professor.
Yeah. Thanks, guys.
Professor, I had a quick question.
Sure. What's up?
For the series thermal circuit that was set up earlier,
Mhm.
when you said that it's something, I think it was the heat transfer is constant.
Yeah.
Is there an assumption for that to be the case?
Yeah. So that's a good point, actually. And so it's in order for that to be the case, you kind of have to assume that the outsides of this block right here are insulated, right? And so kind of what we didn't say was that, on the outsides here, you have kind of perfect insulation. And so in those cases, there's basically nowhere else for the heat to go. So it can't escape out the outsides. The only direction it can go is this way, right? And so if you kind of measure the heat transfer going here, that's going to be the same, heat transfer between these two blocks, which is going to be the same between these two blocks, right? But yeah, you have to assume that there's no heat loss out the outside. Yeah, good point.
Okay, thank you.
Mm-hmm.
No, Professor?
Yep. Mm-hmm.
Is there ever a case where you can, well, probably wax would fall under it, but like have like a dynamic heat transfer? So let's say you want a material that is very conductive in the beginning, but later on poorly conductive later on.
Ooh, you mean like something where the the material properties change as a function of time?
Yeah.
It is possible. So these material properties, they're kind of the same as like, density for fluids or viscosity. And so they can be changed. So they're usually functions of, ironically enough, temperature. And so actually, if you heat up a material enough, then, its thermal conductivity will actually change. And so I can imagine, there's cases where you can manipulate that fact so that, depending on the temperature of the thing or of the material or some other properties, its thermal conductivity can go up or down. Yeah.
So what would superconductors fall under? Would they fall under like going from like a very like non-conductive to very conductive, or is it the other way around?
Yeah, that's a good question. Question that I don't know the answer to. So I don't know that much about superconductors, but definitely that's definitely something I can look up and we can talk about it more in office hours.
Okay, thank you.
Mm-hmm.
Have a nice day.
Thanks, you too. Melanie, did you have any other questions?
No.
Okay, so I'm going to end the Zoom call then. So I'll see you on Wednesday.